Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. In our last episode, we walked through the compelling, multi-source evidence that something invisible makes up roughly 95% of the universe, dark matter accounting for the galaxy rotation curves and gravitational lensing observations, and dark energy driving the accelerating expansion of the cosmos. The evidence is real, independently confirmed, and not seriously disputed by mainstream science. But what dark matter and dark energy actually are remains completely unknown. And that gap, between knowing something must exist and having no idea what it actually is, has generated some of the most creative, most controversial, and most genuinely interesting theoretical debates in all of modern physics. Today, we're walking through all of it, from the serious alternative to dark matter that has real scientific support, to the fringe theories, to what the next generation of experiments might finally be able to tell us. The most scientifically credible alternative to dark matter isn't a conspiracy theory or fringe speculation, it's a research program called Modified Newtonian Dynamics, or MOND, first proposed by physicist Mordechai Milgram in 1983, and developed into more complete theoretical frameworks by several researchers since. The basic idea behind MOND is this: rather than adding invisible mass to account for the anomalous galaxy rotation curves Vera Rubin and others observed, what if our equations for gravity are slightly wrong at very low accelerations, the kind of extremely gentle accelerations experienced by stars at the outer edges of large galaxies? If the gravitational force law behaves slightly differently from the standard Newtonian prediction in this very low acceleration regime, the observed rotation curves could be explained without requiring any dark matter at all. MOND has had genuine successes. It predicted the rotation curves of a wide variety of galaxy types with remarkable accuracy using only the visible matter distribution, without needing to add any free parameters to fit each individual galaxy. This predictive success is significant and has kept MOND as a legitimate research program rather than a fringe idea. However, MOND faces serious challenges when applied beyond individual galaxies. It struggles to account for the large-scale structure of the universe, the detailed pattern of the cosmic microwave background radiation, and in particular the bullet cluster observation we covered in Episode 1, where the gravitational lensing signal was clearly spatially separated from the visible matter distribution in a way that MOND finds very difficult to explain, without invoking additional mass in some form. Most cosmologists consider these large-scale failures serious enough to prefer the dark matter hypothesis, but MOND's galaxy-scale successes mean the debate remains genuinely open in the research community. Like, subscribe, and hype the video. And let's move to the theories that go considerably further from mainstream science. This is where we move from legitimate scientific debate into claims that circulate primarily in conspiracy and alternative science communities rather than in peer-reviewed research. The most common version of this claim is that dark matter is simply invented, a fabrication by mainstream physics to protect a flawed theoretical framework, rather than admit that our understanding of gravity or the early universe is fundamentally wrong. This claim misrepresents how dark matter came to be accepted in mainstream science. Dark matter wasn't invented to protect any existing theory. It was proposed precisely because the existing theories couldn't account for observations. The independent confirmation of dark matter's effects from multiple completely different measurement techniques, galaxy rotation curves, gravitational lensing, the bullet cluster, large-scale structure formation, and the cosmic microwave background, each using entirely different instruments and methodologies, is difficult to explain as a coordinated theoretical bias. Each of these independent lines of evidence would have to be wrong in a different, specific, coordinated way for dark matter to be entirely a fabrication. The distinction between "we don't know what dark matter is" and "dark matter doesn't exist" is a crucial one that these claims tend to collapse. Not knowing the nature of something is very different from that thing not existing. We had compelling evidence for the existence of the neutrino decades before we detected one directly, and the history of physics is full of examples where the evidence for something's existence preceded a direct detection by years or decades. One of the more elaborate alternative frameworks that often gets attached to dark matter skepticism is called the electric universe theory, or plasma cosmology. A set of claims proposing that electromagnetic forces, rather than gravity, are the dominant force shaping the large-scale structure of the universe, and that dark matter is unnecessary once you account for cosmic electromagnetic effects. Plasma cosmology has a genuine historical basis in real plasma physics research, and some of its early proponents were credentialed scientists. However, the specific claims about electromagnetic forces dominating cosmic structure at large scales are not supported by the quantitative evidence. Gravity dominates over electromagnetic forces at the scales of galaxies and galaxy clusters for well-understood reasons. Unlike gravity, electromagnetic forces can be both attractive and repulsive, and the net electromagnetic effect on large, electrically neutral structures averages out rather than producing the consistent large-scale attraction that shapes cosmic structure. Additionally, the plasma cosmology framework has not produced quantitative predictions that match the observed large-scale structure of the universe at the level of precision that the standard dark matter cosmological model achieves. This doesn't mean electromagnetic effects are irrelevant in astrophysics. They're important and active in many contexts. But scaling them up to replace dark matter as the dominant structural force of the universe requires claims that go well beyond what the evidence currently supports. Like, subscribe, and hype the video, and let's talk about what might actually be coming next in this search. The search for dark matter and a deeper understanding of dark energy isn't stalling. It's entering one of its most ambitious experimental phases, with several major new instruments coming online in the coming years specifically designed to push the boundaries of what we can observe and test. The Vera Rubin Observatory in Chile, the same telescope we mentioned in our Planet 9 episodes as the most promising instrument for confirming or ruling out that hypothesis, will conduct the legacy survey of space and time, photographing the entire southern sky repeatedly over 10 years with unprecedented depth and precision. This survey will produce one of the most detailed maps of large-scale cosmic structure ever assembled, which will constrain dark matter distribution models with far greater precision than currently available. The Euclid space mission, launched by the European Space Agency, is specifically designed to map the large-scale structure of the universe and the distribution of dark matter through weak gravitational lensing across billions of galaxies, with the goal of measuring the properties of dark energy with an order of magnitude improvement in precision over current measurements. Underground dark matter detectors continue to grow in sensitivity. Next-generation experiments like the Lux-Zeppelin detector and its successors are probing dark matter interaction, cross-sections multiple orders of magnitude below what previous experiments could reach. If dark matter particles interact with ordinary matter at any currently theoretically plausible level, these experiments have a genuine chance of detecting them within the next decade. Here's a question worth sitting with for a moment, because it has implications beyond just particle physics. What would it mean if the next generation of experiments, more sensitive than anything that has come before by factors of 10 or 100, still returned no detection of dark matter particles? It would mean one of several things, each of which has profound implications for physics. It might mean dark matter particles exist, but interact even more weakly with ordinary matter than our most conservative theoretical models predict, making them real but essentially undetectable with any foreseeable technology. It might mean that modified gravity approaches like MOND, despite their large-scale difficulties, contain some truth that needs to be incorporated into a new theoretical framework we don't yet have. Or it might mean something even more fundamental, that the universe's dark sector involves physics so different from anything in our standard model that we need genuinely new theoretical concepts, not just extensions of existing ones, to describe it. Any of these outcomes would represent a profound development in science, not a failure, but a major constraint on what the answer could be. The null result from decades of WIMP-based searches has already forced the field to broaden its theoretical imagination significantly, and that broadening has produced new ideas and new experimental directions that wouldn't have existed without the pressure of repeated non-detection pushing researchers toward creative alternatives. So here's where the search for the invisible universe actually stands. Dark matter and dark energy are almost certainly real, based on independent lines of evidence from multiple completely different measurement techniques. Modified gravity approaches like MOND capture something real about galaxy-scale dynamics, but struggle at larger scales. The fringe claims that dark matter is simply invented misrepresent how it came to be accepted and what the evidence actually shows. And the next generation of experiments will push our detection capabilities to levels that should either find something or conclusively narrow the theoretical landscape in ways that reshape the entire field. 95% of everything that exists remains invisible to us. That's not a failure of science. It's one of the most extraordinary open frontiers in the entire history of human knowledge. And the people working on it are some of the most creative, most rigorous minds in physics today. If you've made it through both episodes, let me know in the comments what you think dark matter actually is. Like, subscribe, and hype the video, and I'll see you in the next one.